All right, so the dot product here comes from having two vectors, which we defined as v and w, as a1i and b1j. And then for the w, it's a2i and b2j. So then the dot product for us, and the way that we represent the dot product is v with actually a pretty big dot for dot product. So v dot w, the way we say it is v dot w. So the dot product is nothing more than the horizontal components, a1 times a2 plus b1 times b2. So this is the definition of the dot product for us. So we are multiplying the scalars in the horizontal direction, and we're multiplying the scalars in the vertical direction. So notice that the dot product is going to give you a number. All right, it's a number answer. The dot product will give you a number given two vectors. So we're going to multiply horizontal, multiply vertical components, and add them together. That's going to be the definition of our dot product. So I should write down dot product here for you. It's a great question, and I will get to that in box number 3. It's like, what do you use this for? It's awesome things. So let's just do some examples of basic finding the dot product. So if I give you vector v, 6i minus 4j, and vector w, which is negative 4i plus 5j. We're going to find what is v dot w. What's the dot product v dot w given these two vectors?
Negative 44.
Yeah, negative 44, exactly. So we're going to do 6 times negative 4 plus negative 4 times 5, which gives us our negative 44. That's true. So notice dot product can be negative. No big deal. Dot product is just a number for right now. That's all we know about it. Okay, what about example B? What do you think w dot v is going to be? Is this going to be the same thing?
Yes.
If you had to take a guess, what do you think?
Yes.
It is the same thing, right? Because multiplication is commutative. So we'd end up with just negative 4 times a 6 plus a 5 times a negative 4, which of course, again, is negative 44. So these two examples illustrate that v dot w is the same thing as w dot v. So dot products are commutative, right? They move back and forth. All right, question then, what do you think? What is v dot v? V dot with itself, the dot product of v and itself. You can actually do that. Well, that's going to be the, that's going to be, if you look at the components for this one, right? We're looking at this one here. So it's going to be 6 times a 6 plus negative 4 times negative 4. What would that be? I'm getting 52, yeah, 52. Okay, so I'm getting 52 with that one. All right, so here's the question I have for you. What's the magnitude of vector v? Yes, okay, so how'd you do that so fast? Yeah, the square root of 6 squared plus negative 4 squared. So we're getting the square root of 52. Are these numbers close? They're very close, right? How do I make the magnitude look like the dot product? What would I have to do? Or what's another way of doing that? Yeah, very good. So here's what we're learning with this. V dot v is the same thing as magnitude squared. That's important. So we'll put a box around that. We'll highlight that one. Okay? V dot with itself is the same thing as magnitude squared. So we've learned a couple of things from this example. All right, so there's 5 properties for the dot product that we need to be responsible for. We actually just saw 2 of them in the work that we just did. So if we're given vectors u and v and w, and we'll say c is a scalar, then we've noticed that u dot v is the same thing as v dot u. So it's commutative. That's no big deal. We also saw that a vector dotted with itself is the same thing as that vector's magnitude squared. So those 2 are the ones we just saw in the last example.
Is the u like in the w?
No, v is a vector, v, u, and w are vectors.
Oh, so okay, so you now you have 3.
Yeah, because I'm going to do another one down here. And then c is a scalar. Okay, so there's the first 2. Third one, let's say I have u dotted with the product or the addition of v plus w. So I'm going to add two vectors together and then take its dot product. That's what that says. Add v and u, and then take the dot product of that. Well, it's the same thing as taking u dot v plus u dot w. So what does that represent there? What property? Where's the D?
Associated?
Yeah, so distribution property, right? It also works for vectors. This one's very straightforward. 0 dotted with any vector. What do you think? Take a guess. Yep, sure is. And the last one. Let's say you have a scalar times a vector u, and you want to dot that with v. So scalar times u dot v. I'll move it up a little bit. That's the same thing as scalar times u dot v. So that means, what is that looking like? There's another property that we all know and love, starts with an A. Associative, very good. And this is the same thing as u dot scalar times vector v. So it doesn't matter what you do, no matter how you do it, scalar times u dot v will any of those three be the same. Okay? All right. This is where the graph paper comes in handy. Not necessary if you don't have it, but don't worry about it. So I have two vectors in the plane that we've just drawn. I have vector v, which is components 4i minus j. And then I have vector w, which is negative 2i plus 3j in the coordinate plane. And here is what I'd like you to take a guess on. You see this angle here between these two? We're going to call that angle theta. I would like you and your table to come up with your best guess as to what you think that angle is. Wow. So check out our guesses there. We have 125, 136. So these are our guesses based on this angle, okay? One of the applications of dot products enables us to find the angle between two vectors. But notice that there are two angles between this vector, right? There's this little angle, and then there's this angle on the outside. Well, the thing that we're about to do is always going to find the smaller of the two. Okay? So we're going to find that angle between two vectors. Now, I'm not going to show you the proof. It's in the book if you want to check it out. But if I were to connect this line to that line, could you see a triangle there?
Yeah.
And could you see this angle? This is the one that we're looking for. Is that true? Yeah. And if I knew all three of those sides, I'd have a side triangle. And I could use the law of what for side? No. Law of cosine, something that was on your quiz, right? That everybody knows and loves. Okay. So here it is. So I'll say from the law of cosines. From the law of cosines, we can actually figure out that angle. And it is the cosine of theta, which is why it's important that we know it comes from the law of cosines. Cosine of that angle is nothing more than v dot w divided by magnitude v times magnitude w. That's it. That's an important information, or that's an important piece of information for us. All right, so we need the cosine of that angle is the dot product divided by the product of the magnitudes. So what three pieces of information do we need? Let's get the dot product. Yes, we need the dot product. We can do it together real quick. So what would v dot w be in this case? Well, it'd be 4 times negative 2. I got something else. Plus, that's what I got. 3 times the negative 1. So the dot product I'm getting as negative 11. Got it. What else do I need? I need the magnitude. So what's the magnitude of vector v? Well, it's the square root of 4 squared plus a negative 1 squared. So I'm getting the square root of 17. Good. What else do I need? I need the magnitude of vector w. So I need the square root of negative 2 quantity squared plus 3 quantity squared. So I'm looking at the square root of 13. All right, you guys, I have all the pieces that I need. I have all three of my pieces. So I'm going to move this up and plug it in. So the cosine of theta has to be the dot product, which was negative 11, divided by root 17 times root 13. Well, we can simplify this expression. So cosine theta is equal to negative 11 over square root of 221, I believe, if that's right. 17 times 13. But we don't want don't want the cosine of that angle, do we? What do we want, you guys? We actually want the angle. So how do we get just the angle then? What do we do? The inverse cosine. Very good. So inverse cosine of negative 11 over square root of 221. Did I do that right? 17 times 13, is that right?
You don't want to rationalize it yet?
No, because all we're going to do, we're going to plug this in the calculator and get it. I'm going to show you how to do that right now.
42.27.
Play, and we'll throw this down here. Okay, here we go. So if we're asking the calculator, are we finding a degree or a radian, you guys? We're finding a degree, so what mode should we be in? So make sure that you're in degree mode, because we want a degree. Second quit. So we're doing second inverse cosine of negative 11 divided by the square root of 221. Close parentheses, bam. 137.7 degrees. Who guessed that? Holy cow.
That's us. Oh.
Who guessed 137 degrees?
It's not gonna be 137 degrees.
Wow, that's crazy, man. You guys are really, really close. 137, 135, 136. That is actually pretty darn close. All right, so here's your two vectors. I want you to draw those two vectors in the coordinate plane, make a guess as to what you think that angle is, and then compute the angle. And remember that this formula right here will always give you the smaller of the two angles. Okay? That's what I'd like you to do right now in your table groups.
Wait, then what am I supposed
So
to
you
do?
got, 100.3 degrees on that is what you should have gotten that one.
100.3?